All right, starting off, we're going to be covering chapter 20.2 today, a brief excerpt from stuff that you'll be using quite a bit if you take Chem 2. Before we do that, I wanted to remind us of our rules for oxidation numbers because we're going to be using those at least a little bit for our chapter 20.2 material. So our rules for assigning oxidation states or oxidation numbers, we follow these rules in priority, so we're supposed to follow them through in this order. A lot of the time they don't really overlap, and so it's kind of generally just do stuff on this first slide and then do stuff on the next slide after. So if we have free elements, things that are in their natural state, they get an oxidation state or number of 0. So if it's just one element by itself and there's no charge, it gets an oxidation state of 0. If it's an ion that's by itself, then it's got an oxidation state equal to its charge. The sum of the oxidation states of the atoms in a neutral compound is 0. That's the same as the charge. Or for an ion, if it's a polyatomic ion, it's going to equal the charge of the ion. So whatever the numbers are for each of the individual components is dependent on what the overall charge is. When metals are in compounds, they have a positive oxidation state equal to their ion charge. So our sodium here being plus, so it has a +1 oxidation state. Our calcium being 2+, so it gets a +2 oxidation state. And then in their compounds, nonmetals have oxidation states according to the table that we see here, where we have fluorine, hydrogen, oxygen getting the oxidation state that matches with what their charge would be. So for fluorine, fluorine's normally F- when it's an ion, so it takes a -1 oxidation state. Hydrogen +1, oxygen -2. Our group 7A, that's our halogens, -1. Group 6A, -2. Group 5A, -3. And these are the same as the charge that these elements would take if they were in their ion state. And the other thing that we want to cover or review is we've got some definitions for oxidation and reduction, and our newest one, this was our third definition, there were two others, but our third one is that oxidation is when we get an increase in our oxidation state, so when our oxidation number goes up from the left side to the right side. So in this case, it's the carbon going from a 0 to a +4. That's our oxidation portion. And then the thing that's being reduced is having a decrease in its oxidation state. So sulfur is going from a 0 to a -2. So carbon is being reduced or is undergoing reduction because the oxidation number has gone down. The oxidation number has been reduced. Okay, so jumping on to chapter 20, just a short excerpt from chapter 20 covering redox reactions. So in redox reactions, we've got two mnemonic devices. One of them is oil rig. Oxidation is losing. This was, I think, our second definition. Oxidation is losing. And the part that we have to remember for this is that it's electrons. And then the rig part, reduction, is gaining electrons. And here we also have that our oxidation is an increase in oxidation state. This is why we covered our oxidation numbers. Reduction is a decrease in oxidation state. And so to figure out our oxidation and reduction portions of our reaction, we have to go through and assign individual numbers, oxidation state numbers, to each of the elements that's in our reaction. When we are doing redox reactions, we also need to be able to balance redox reactions, and that's all that we're doing in this excerpt of the chapter. So normally we were just balancing for mass. When we're doing redox reactions, we also have to balance for charge, and this adds a couple of extra steps. And so the way that we are going to do this is we're going to break our equation into two half reactions. We're going to separate our oxidation half reaction from our reduction half reaction. So in this case, we would be pulling out Ca goes to CaOH2, and that would be one half reaction. We would write that out separately by itself. We would balance the left and the right sides for both mass and then charge. And we would also have our reduction half reaction. So our H2O going to H2, we would pull that out and make that a separate half reaction. We'd usually do them side by side the way that I do them. We would balance it for mass, so looking at each of the individual elements, and then we would also balance it for charge, so thinking about electrons. Here's the procedure for balancing half reactions for redox reactions in an acidic solution. Everything that we do is going to be based on acidic solution. We'll also learn how to balance in basic solution, and the way that we're going to do that is by starting balancing it in acidic solution, and then we'll make one little change at the end. So the first thing that we need to do is we need to assign oxidation states, things like +1, -2, -4, +3, whatever our numbers are, and identify the substance as being oxidized and reduced. Remembering that our oxidized substance has the number going up and our reduced substance has the number going down. So figuring out which of our elements is being oxidized, oxidation state number going up, which is being reduced, the oxidation number or state is going down. Then we're going to separate the reaction into the two half reactions. We'll have an oxidation, and we'll also have reduction. I usually set them up side by side, and then we can work through them together at the same pace. Once we've got those separated, then we're going to balance the half reactions with respect to mass. And with respect to mass is what we've done before. Plus some other steps. So the first step is balance all the elements other than hydrogen and oxygen. That's sort of like what we've done in the past. So balancing things like nitrogen, any metals, any nonmetals that are not hydrogen and oxygen. And then to balance out our oxygen, we add H2O. We can add H2O to either side because there's lots of water in a solution. So if we're in an aqueous solution, there's water literally all over the place. We've got essentially unlimited amount of water. So we can just say we've got some water on the left side or we've got some water on the right side because it's in the solution. And then when we balance it by adding H2O, chances are we're going to upset our balance of hydrogen. We can balance our hydrogen by adding H+. There's going to be significant amounts of H+. In acidic solution. An acidic solution means that we have extra H+ floating around as opposed to OH-, which would be base. Once we've got everything balanced with respect to mass, so balancing things that aren't hydrogen and oxygen, balancing our oxygen by adding H2O, then balancing the H by adding H+, then we can balance it with respect to charge by adding electrons. The tricky part about adding electrons, what charge do electrons have? What charge does an electron have? -1 or 1 minus. So we're adding negative charges, so we have to bring down the bigger charge. So whichever side is more positive, we're going to bring that charge down by adding electrons to that side. This is not normally how we do it. Normally we're increasing the number with our mass. So this is opposite. It's common to make mistakes doing, honestly, any of these steps, but I feel like this step, there's also a lot of issues. Then, once we've got both of our half reactions balanced, we did them side by side. Once we've got both of those balanced with respect to mass and with respect to charge, then we need to make it so that the number of electrons are equal. So we are going to multiply one or both reactions so electrons are equal. Sometimes we don't have to multiply either of them. Usually we'll have to multiply at least one of them. Sometimes we have to multiply both of them. One of the reactions should have electrons on the left side. The other one should have electrons on the right side. So one should have electrons on reactants. The other should be on the products side. If that's not the case, something went wrong. So that's a way that we can potentially check that we did things correctly, or at least look for a possible mistake. Once the number of electrons on both sides is equal, so one on the reactant, the other on the product, we can add the two half reactions together. We're going to cancel out electrons and other species, other chemicals, as necessary. The electrons should always cancel completely. If you end up with extra electrons, something went wrong. And then, finally, we can verify that the reaction is balanced with respect to mass and with respect to charge. And unlike with our previous reactions where we've balanced stuff, where we kind of just said, we probably did it right, you always want to check. Always go back and double check for redox reactions. There's a lot more moving pieces when we are doing the half reaction method for redox equations. It's important that you go back and double check because you will probably make a mistake. Unless you're very, very diligent along the way, there's a very good chance that you will make a mistake somewhere. So looking at essentially our most basic form of a redox reaction, and we've got the steps over here on the right side, just shortened. So our first step, we want to assign oxidation states. So we have to refer back to our 5-step list. Our first rule on that list was we assign anything that's by itself in its normal natural state a number of 0. So that's going to be our aluminum on the reactant side and our copper on the right side. Our second rule, I believe, for assigning those oxidation states, things that are monatomic ions like copper 2+ and aluminum 3+ get the same charge or get the same oxidation number as their charge. So copper is going to be a +2, aluminum is going to be a +3. All right. Then we can, now that we've got our oxidation states assigned, we need to separate them into our two half reactions. It is also good practice for us, preparing us for the exam, when I'm going to ask us to label them as reduction and oxidation half reactions to identify which one's being oxidized and which one is being reduced. Aluminum starts from a 0 and goes to a +3. How did its oxidation state change? It went up, and so aluminum was oxidized. So aluminum as a solid going to aluminum ion. Aqueous, this is our oxidation half reaction. And then copper is going to be reduction. It's going from a +2 to a 0, which is a reduction in the number, and also means that copper is being reduced. So copper 2+, AQ going to Cu as a solid. This is our reduction half reaction. We would then balance the half reactions with respect to mass, since we've just got aluminum, 1 on each side, and copper, 1 on each side. We don't have to do that step. It's already balanced. This is about as simple as you could make a redox equation. We then need to balance our half reactions with respect to charge, which we have not previously done. So looking at charge, I'll just write number. Our left side we've got 0, our right side we've got 3+. For our reduction half reaction, we've got 2+, and we've got 0. What can we add in to change our charge? How can we change our charge? It's adding electrons. So these are adding electron steps. So we're going to add electrons. Which side are we going to add electrons to for our aluminum half reaction? Are we going to add electrons to the left or to the right? I'll give you a moment to think about it. The correct answer is to the right. The reason that we're adding the electrons to the right side is because electrons have a negative charge. To balance out a 3+ charge, to bring 3+ down to 0, how many electrons do we need? We need 3 electrons. That's adding a -3, 3+, and a -3. It's now 0 on both sides. For our copper, or reduction half reaction, which side do we need to add the electrons to? We need to add it to the reactant side. And we have to add 2 to balance out the 2+ charge. Notice that for our aluminum half reaction, we added the electrons to the right side. For our reduction or copper half reaction, we added them to the left side. So we now have them on opposite sides. That means when we add them back together later, we'll have the same number of electrons on both sides. They'll cancel out and disappear. And that's what we want. So if you somehow in your brain got it screwed up, got it mixed up, got it backwards, we added the electrons to the right side, they're never going to cancel out. And that would be assigned to you, hopefully, something that you would pick up where you're like, I must have screwed up somewhere. Now we need to make the number of electrons equal. So we need our oxidation half reaction and our reduction half reaction to have the same number of electrons. What do we need to multiply our oxidation and reduction equations to get them to be equal? What do 2 and 3 both go into? 2 times 3, 6. Is that least common multiple? I think that's what we called it. LCM. That's the smallest number that 2 and 3 both multiply into. So our oxidation half reaction, we need to multiply by 2. So this 2 times 3 will get us to 6. Our reduction half reaction, we need to multiply this 2 by 3 so that it gets up to 6. And this is one of the common places where we'll screw up. This is usually where I screw up. You forget to distribute the number to every single thing in the half reaction. So we're going to have, for our oxidation, 2 aluminum going to 2 aluminum ion plus 6 electrons. And then for our reduction, we're going to have 6 electrons plus 3 times 1 copper, 3 copper ions, goes to 3 times our copper as a solid. And then we add the half reactions together. A little short on space, so I'm not going to rewrite them over each other. That's usually what I would do. So 2Al as a solid. I'm going to be lazy and duplicate everything. You can write these, by the way, in any order you want. So you can write the aluminum on the left, because that's the thing that we had on the left. You can write the electrons on the left, and then the aluminum, and then the copper. You can do it whatever order you want, just as long as you don't get the left side and the right side mixed up. And this is going to go to everything that's on the product side. And then we need to cancel anything out that's common on both sides. In this case, that's just our electrons. So we'll cross out our electrons. And then for us, for the verify part, we would probably just check the mass. So 2 aluminum, 3 copper on the left, 3 copper on the right. So this should be all balanced. Questions about any of that process? Pretty much all that we did that was new for this, we separated the oxidation, the reduction, and we also balanced with respect to charge, which we haven't done before. So adding those electrons in, and then getting the electrons to cancel out. Because electrons, just by convention, we ignore in most of our balanced chemical equations. All right, one with a little bit more to do maybe. Balance the redox reaction in acidic solution, which is the one that we know how to do. So we need to start off by assigning oxidation states. So go ahead and assign oxidation states for our 4 chemicals, and then separate them into their 2 half reactions. All right, first step, assign oxidation states. We've got things that are by themselves. Those things are chromium and hydrogen. So those both get numbers of 0. We also have some monoatomic ions, our hydrogen ion and our chromium 2+ ion. Our hydrogen ion, because it's a 1+, gets a +1 oxidation state. Our chromium gets a +2 oxidation state to match its 2+ charge. We then want to separate them into our half reactions, our oxidation and reduction half reactions. Our chromium is going from a 0 to a +2. That's an increase in its number. That means it's being oxidized. So our oxidation half reaction is Cr solid going to Cr2 plus aqueous. And then our hydrogen is being reduced, so our reduction half reaction is going from a +1 to a 0. That's reducing the number, which is a reduction. So H plus AQ goes to H2 as a gas. Our next step is that we need to balance the half reactions with respect to mass. For chromium, it's already balanced. We've got one chromium on the left, one chromium on the right, so there's nothing to do there. Already balanced for chromium. For our reduction half reaction, for hydrogen, we've got one on the left, two on the right. To get those to balance, we need a 2 in front of our hydrogen ion on the left, and now they're balanced. So that's balanced with respect to mass. We also need to balance them with respect to charge. So to balance them with respect to charge, we're going to look at the charge as I'm writing it in as a number. For chromium, Cr by itself, that's a 0. For our chromium 2 plus ion, that's going to be a 2 plus. How many electrons do we need, and where are we going to add them? We need 2 electrons. We need to add them to the right side. Because electrons are negatively charged, we're going to bring down the energy on the right side. So plus 2 E minus is adding 2 negative charge. So that neutralizes the 2 plus charge. What about our charge for our reduction half reaction? How much charge do we have on the left side? 2, because we've got 2 H plus ions. And so our charge on the left side here is 2 plus. Our charge on the right side is 0 because we've just got neutral hydrogen. So to balance out this 2 positive charge, we need to add in 2 electrons on the left side. And that'll balance out the positive charge, so both sides are neutral now. Conveniently for us, the number of electrons are also equal. So we've got, for our reduction, 2 electrons on the left side. For our oxidation, 2 electrons on the right side. So we can just add the half reactions together. So Cr solid, and then 2 electrons are 2 hydrogen ions. Our arrow, the stuff that's on the right, Cr2 plus. Plus 2 electrons. Plus H2 gas. And then we can cancel out anything that shows up on the left side and the right side. This will always, if we've done things correctly, this will always include our electrons. The electrons should always cancel out. And then we can go back through and verify. You can also do this with charge. I didn't show us that on the last step, but let's do that for this one. So looking at our chromium on the left, we've got 1. On the right, we've got 1. Looking at our hydrogens on the left, we've got 2. And on the right, we've got 2. Looking at our charge on the left, no charge from our chromium. 2 times the plus gives us a 2 plus on the left side. Our H2 doesn't contribute any charge. Our Cr2+ contributes 2 positive charge. So our charge is also balanced. And that's what we want to see. Everything should be equal on both sides. We have 2 more examples balancing in acidic solutions. We're going to up the difficulty a little bit. So we want to balance this redox reaction in acidic solution. The first thing that we need to do is set our oxidation numbers. In this case, we don't have anything that's neutral. We've got everything charged. So we're not assigning zeros to anything, but we do get to assign some charges to our monoatomic ions, our iron 2+, our iron 3+, and our manganese 2+. They get +2, +3, and +2 respectively. And then we have to do a little bit of math to figure out what our manganese is going to be. Our manganese oxide. Permanganate. We've got MnO4-, so we've got an overall of -1. Our manganese is going to take whatever charge it would have as an ion here. So we have to figure out what that's going to be. We've got 4 oxygens. What's the charge on oxygen normally as an ion? -2. And then whatever our manganese is going to be the X here. So 4 times -2, we've got a -8. X minus 8 equals -1. If we add 8 to both sides, X equals +7. So our manganese gets +7. The oxygen has its preferred -2. And then we get to separate them to reduction and oxidation half reactions. Iron's oxidation number is changing. It's going from a +2 to a +3. What is that going to be? Oxidation or reduction? Oxidation, because the number is going up. It's got a bigger oxidation number. That's oxidation. So our oxidation half reaction, Fe2+, goes to Fe3+. That means that our reduction half reaction is going to be the other thing. Our permanganate going to manganese 2+. So we've separated our half reactions. Our third step is that we need to balance with respect to mass. For our oxidation half reaction, this is easy. We've got 1 iron on the left, 1 iron on the right. So that one's already balanced, nothing to do. For our reduction half reaction, we balance everything that's not oxygen and hydrogen first, so that's going to be our manganese. This is balanced. We've got 1 and 1. And now we get to do the new steps, the stuff that's new to us for redox reactions. So we're going to balance oxygen first. We currently have 4 oxygens on the left side. We're doing this balancing in an acidic solution, an acidic aqueous solution. Aqueous means what? What's aqua? Water. So we're in a water solution. We've got tons of water around, and so we can just say, all right, well, we can balance this 4 oxygens by adding water. The formula for water is H2O. There's 1 oxygen in each of those, so we're going to need 4 of them. 4 H2Os on the right side will balance out the 4 oxygens in our permanganate ion. Is everything balanced now? It's not, right? Because we added in hydrogens. And so now we have hydrogen to balance. How many hydrogens do we have on the right side? We have 8. 4 times 2 is 8. How many do we have on the reactant side? We don't have any. But we're in acidic solution, and acidic means that we've got extra H plus floating around, which is super convenient for us because H plus will balance out our number of hydrogens. We need how many hydrogens? We need 8. So we're going to add 8 H plus, and now our hydrogens are balanced. Is there anything else we need to balance? Not for mass, right? We're done balancing for mass. Now we need to balance for charge. So balancing for charge, we'll do our oxidation half reaction first. Our charge on the left side is +2. Our charge on the right side is +3. To get our +2 and our +3 to have the same number, we need to add electrons. So we're going to add 1 electron to the right side because our electron has a minus charge. 1 minus, 3 plus. This brings us down to 2. Drawing my pluses and minuses on the wrong side. Whatever, they're balanced. Now we get to do it for our reduction half reaction. Let's go through and add up our charges. We'll do the right side first because that's the easier one. We've got 2 plus from our manganese ion. The left side, we've got a 1 minus from our permanganate, and we've got 8 1 pluses from our hydrogen. So 8 plus 1 minus. The left side is 7 plus. How can we get 7 plus and 2 plus to be the same? Which one of those can we change to make it the other one? What are we going to add? Electrons. Electrons have what charge? Negative charge. We do need 5 of them. We need to add them to the left side. We have to bring this 7 plus down. So we're going to add 5 electrons to the left side. So now we've got the 5 minus from our electrons. We've got the 7 plus that we had before, which brings it down to a 2 plus. We should now be balanced with respect to charge. The next step is we have to prepare for adding these together. So the reason that we separated them out is so that we could balance the charges separately. This is easier than balancing it all together. But we need the number of electrons to be equal in our oxidation, which is going to have the electrons on the right side, and in our reduction, which is going to have them on the left side. So we need the least common multiple of 5 and 1. What do 5 and 1 both multiply into? 5. Since our reduction half reaction is already at 5 electrons, we just multiply our oxidation half reaction by 5. So we're going to have 5 Fe2 plus going to 5 Fe3 plus 5 electrons. And then we get to add that to our reduction half reaction. And I'm going to write them on top of each other. I'm omitting the state symbols. And I'm being lazy in another way. I'm not changing all the colors. Doubling down on being lazy. Copy paste. So if you write them over top of each other, we're going to collect everything that's on the left side and just add those together, write them out in one line. Everything on the right side, we'll write those out in one line. And then things that are the same on both sides, in this case that's just our electrons, those are going to cancel out on both sides. So our electrons cancel, and our final 8H plus MnO4 minus plus 5Fe2 plus goes to 5Fe3 plus manganese 2 plus and 4 H2O. That would be our step 6. And then the last step, which we do want to do because it's redox reactions, we want to check and make sure that everything's balanced on both sides. I'm going to just do that verbally for balancing for mass, and then we'll look at the charge with the numbers written out. So for hydrogen, we've got 8 hydrogens on the left side. On the right side, we've got 4 times 2, which is 8 hydrogens. Hydrogens are balanced. For our manganese, we've got 1 on the left side, 1 on the right side. Manganese is balanced. Our oxygen, we've got 4 on the left side. We've got 4 times 1 on the right side. Oxygen is balanced. 5 irons, iron is balanced. So everything with respect to mass is balanced. And now we'll just double check for charge. We've got 8 times 1 plus. So that's 8 plus. Should write that over here. Our permanganate, we've got 1 minus. Our 5Fe2 plus, we've got 10 plus. So we've got 10 and 8, and then a 1 minus. So 18 minus 1, 17 plus, which is kind of crazy. On the right side, we've got 5 times 3 plus for 15. And then our manganese is a 2 plus. The water is neutral, so this is also 17 plus. So our charge is balanced. So unless we screwed up in our double checking, we didn't screw up when we were doing the actual balancing. Do we have questions or confusion so far? We have one more for acidic solution. Would you like time to work through this by yourselves? Or do you want me to just walk us through it again? Okay, I'm going to just walk us through it again because we do have in basic solution as well. Does anyone remember what our first step is? Oxidation states, that's correct. So we're looking at what are the oxidation states for everything in our reaction. We've got copper by itself, so that gets a 0. That's the only thing that's by itself in its normal natural state. So that would be our first rule for our oxidation numbers. For our second step for oxidation numbers, monoatomic ions. So our Cu2 plus gets assigned a +2. Our third step, the total charge of things that are neutral is going to be neutral. So in our NO2, this has to add up to a 0. Our NO3 minus, this has to add up to a -1. That would be for our third step. Our fourth step, we don't have any metals, so we don't have to do anything with that. Our fifth step is when we deal with nonmetals, so nitrogen and oxygen and nitrogen and oxygen. In these compounds, we go through a hierarchy. Top of the list, fluorine. Then hydrogen. We don't have hydrogen either. then oxygen comes next, and so oxygen gets its preferred -2 for both of these. And then nitrogen has to make up the balance. For NO2, we've got -2 on each of the oxygens. We've got 2 of them. So this is an overall -4. Our nitrogen has to balance out -4, so our nitrogen is +4. In our NO3-, 3 times -2 has to have an overall of -1. So whatever our nitrogen is going to be the x here. So whatever our nitrogen is plus 3 times the -2 or -6 equals a -1. X minus 6 equals -1. Add 6 to both sides. X equals +5. Done with step 1. Step 2, we want to separate them out into their half reactions. Copper is going to be one of our half reactions. Nitrogen is going to be our other half reaction. So Cu going to Cu2 plus, NO3- going to NO2. We should also be able to recognize which one is reduction and which one is oxidation. Nitrogen went from a +5 to a +4. Did its number increase or decrease? +5 to +4. Decrease. It was reduced. So our nitrogen is our reduction half reaction. That would make copper our oxidation half reaction. We could also identify that one first. Its oxidation number went up, and that's oxidation. Now we have to balance both of these with respect to mass. For our copper one, that's easy. Love to see it. We've got 1 and 1. Nice. It's already balanced. For our reduction half reaction, we're balancing everything that's not oxygen and hydrogen first. So that's just our nitrogen. We've got 1 and 1. What do we balance next? Oxygen. For oxygen, we've got 3 on the left, 2 on the right. We need this 2 to go up to balance out with the 3. To do that, we just assume that we can pull in a water. There's unlimited water around because we're in an aqueous solution, so we can do that. So we just say, well, there's probably an H2O on the product side. Reasonable enough. Now what do we balance? Hydrogen, because we just added hydrogen in. Kind of annoying. So we've got 2 on the right side from our H2O that we added. We currently have none on the left side, but we are in acidic solution. An acidic solution means that we've got H plus in excess. And so we can just say, well, there's 2 hydrogen ions floating around in solution. They would really be H3O pluses, but to simplify, we're writing them as H2O, or sorry, H plus. And so now we've got 2 H's on the left side. I wrote that in the wrong spot. There we go. Balance with respect to mass. Now what are we balancing? It's not quite oxidation states. Charge. So we're going to balance for charge. For our oxidation half reaction, I'm going to shimmy this over a little bit. Looking at our charge, we've got 0 on the left side. We've got 2 plus on the right side. We can balance these out by adding in electrons. Electrons don't show up in our balanced chemical equation, so it's not going to throw off our balancing. Redox reactions we can also define with respect to electrons. Oxidation is losing electrons, reduction is gaining electrons. So there's some transfer of electrons going on here. The way that we would do this is we would add 2 electrons to the right side. The electrons have a negative charge. We added 2 of them to balance out the 2 plus. So that balances out our charge. For our other half reaction, the right side is also 0. Nitrogen dioxide and water both have 0 charge. On the left side, we've got nitrate, which has a 1 minus, plus 2 H pluses. So we've got an overall 1 plus. To balance that out, we're going to add 1 electron. I'm going to write it as a -1. And that'll get the charges balanced. So we've got overall 0 and 0 for both of our half reactions. What's our next step? We need to make the electrons equal on both sides. So for our reduction half reaction, we've got 1 electron. Our oxidation half reaction, we've got 2 electrons. So we need to take our reduction half reaction and multiply it by 2. The whole thing. This is so that our electrons cancel. The reason we have to multiply everything is because it's balanced. So if we double everything, it's still going to be balanced, including charge. I'm going to rewrite these. Yeah, I'm going to rewrite these. Cu goes to Cu2 plus 2 electrons. That's our oxidation. And then our reduction. And you have to remember to multiply this 2 by every single thing that's in your reduction half reaction. Otherwise, you're going to screw up somewhere. Okay, so 2 electrons, 2 times 2, 4, H plus 2 times 1 NO3 minus, that's 2 NO3 minus, goes to NO2 plus H2O. Where's the mistake? We have to multiply 2 by everything. And what I didn't do is I didn't multiply the 2 with the NO2 and the H2O. So we need to make sure those also get multiplied. Are we good now? Hopefully. Let's add it all together and then find out with our step 7, our check. So we have an equal number of electrons on both sides, which is what we want, by the way. And so we can cross those out. Those are not going to make it into our final redox reaction. And then we add everything together on the left side, add everything together on the right side. And I'm going to rush through this so that we can get on with the verify part. We'll write it all in one color, so it's a little harder to see. If you have colored pencils or colored pens on an exam, especially if you have the erasable, like the Pilot friction pens on an exam, it might help you to write them with all of the colors because it's easier to keep track of stuff. So this should be our balanced chemical reaction. but we need to go back and check because it's very easy to screw up, and we don't always catch when we screw up, and that's why we need to check at the end. This is one of the ways that we can make sure we didn't screw up. Everything should be balanced at the end. So for our hydrogens, got 4 on the left. We've got 2 times 2 in our H2O for 4. We've also got nitrogen, 2 and 2. We've also got oxygen, 2 times 3 is 6. 2 times 2 is 4, plus another 2 from our water is 6. And we've also got copper, which is 1 and 1. I'll write that really tiny at the top because it's already balanced. And then charge. For charge, we've got 4 plus, 2 times 1 minus, 2 plus. On the right side, 2 plus. Questions about any of those steps? As you can probably see, there's a lot of steps, there's a lot of parts. Redox reactions are not exactly light work until you've practiced them a lot. So spend time working on memorizing our 7-step program, plus the 5 steps for the oxidation states. And because that wasn't enough, we can also balance them in basic solution. There are different methods for doing this. I think there's at least 2 methods for doing this, and one of them is crazy, and we're not going to do that way because that's the one that I don't know how to do. You can find out how to do that by watching videos maybe online. The other way, which I think is less crazy, we add 1 extra step, and that 1 extra step is in our step 3. So we're balancing each half reaction with respect to mass. So normally we balance everything that's not hydrogen and oxygen. We balance everything with oxygen by adding H2O. We balance H by adding H+. But, and this is a big but we are in basic solution. Basic means there's extra OH minus floating around. There's hydroxide floating around. We are not going to have H plus floating around. There is technically H plus probably in solution, but it's a very small amount. Any H plus that we would say that we would have would get used up by hydroxide because it's a basic solution. We've got extra OH minus floating around. So to make this fit with being in basic solution, the 1 step that we add is we're going to neutralize all of our H plus by adding OH minus. The hydroxide is going to neutralize our hydrogen ions. The side that has H plus plus H minus turns into H2O. So that side, whatever side had the H plus, those will just turn into waters. The other side gets, or will have remaining OH minus. Hydroxide. This might end up with us having water on both sides in one of our half reactions. That is fine. We'll just cancel some of those out later. So this is our big singular extra step for doing it in basic solution. What's nice about this is that we basically just memorize one way of doing it. We memorize the acidic balancing, and we add in one extra step to do basic balancing. And it's really quite easy. So this is the way that we do it. All right, let's look at an example. You will also always, by the way, be told that it's acidic or basic solution in the problem. Like, it might say something like this for the problem text: balance the redox reaction in basic solution. If it's on an exam, it'll probably also instruct you to label your half reactions and to write your oxidation numbers for all of the elements. So to start, step 1, assign oxidation numbers. I2 is its normal natural state. So iodine gets a 0. That's the only one of those. We have a monoatomic ion or a monatomic ion, iodide. It gets the same number as its charge. So I minus gets a -1. Our MnO2 and our MnO4 minus, our permanganate and our manganese 4 oxide, will have an overall for MnO2 of 0. For our permanganate, it's going to have an overall -1. We saw this one earlier, so I'm just going to say that it's a +7 and a -2. Manganese here is a manganese 7. And MnO2, the manganese is going to be +4 for its charge. We don't have to do any of that fluorine, hydrogen, oxygen, 7A, 6A, 5A stuff. That would be our step 5 for oxidation numbers. So this is all of our numbers assigned. Now we need to split it into half reactions. So separate all of our iodide stuff, iodine stuff, that'll be one part. All of our manganese stuff, that'll be another part. I minus to I2, permanganate to MnO2. Which one of these two half reactions is our oxidation half reaction? The iodine is the oxidation. It went from a -1 to a 0. That's an increase. That's our oxidation. The other one went from a +7 to a +4 for manganese. That's reducing the number. That's our reduction half reaction. Historically, I've made a question like this 6 points. So one of the ways that you would get points for this question, assigning all the states, assigning oxidation and reduction, and then probably the rest of the points would be for the balancing. So now we have to go through and balance everything. And we want to balance first with respect to anything that's not oxygen and hydrogen. So for oxidation, we've got iodine. We've got 2 on the right. We've got 1 on the left. To get those equal, we need a 2 in front of our iodide on the left side. Iodine's the only thing that we have to balance there, so that's lovely for us. Save us some work. For our reduction half reaction, we have to balance our manganese first. Conveniently for us, though, already balanced. Next, we're going to balance oxygen. So for our oxygen, we've got 4 on the left, 2 on the right. We can balance these by adding water, H2O. If we add 1, then we would have 2 plus 1 is 3, which is not 4. So we have to add another H2O. So make it 2 waters for the table. Then we have to balance hydrogen. How do we balance hydrogen? H plus. We've got 4 hydrogens on the right side, 2 times 2. On the left side currently we've got 0. So we need 4 H plus on the left side. And now our hydrogens are balanced. This is where we add in our 1 extra step. So for our 1 extra step, we're in basic solution. Basic solution means that we cannot have H plus floating around. It's basic, we have extra OH minus floating around. So to make it in basic solution, add OH minus to both sides. We have 4 H pluses on the left, so we need to add 4 hydroxides to both sides. We do that in a different color. How about orange, go Giants? Not New York or San Francisco. COS, Giants. So what this does for us is that OH minus and the H plus on the left side turns into H2O. Is everything balanced? There's one thing that's not balanced yet. Charge. So now we balance charge. So for our oxidation half reaction, what's our charge on the left side? We'll write it as -2. We've got 2 times the 1 minus charge. On the right side, 0. We have to add electrons. Which side are we going to add the electrons to, the left side or the right side? It's got to be to the right side. Electrons have negative charge, so we're bringing the 0 down to a -2. We're stooping down to that -2 level. So we add 2 electrons, -2, -2. We also have to balance for our reduction half reaction. So for charge, we've got waters on the left side. We've also got permanganate, which is a 1 minus. So it's a -1. On the right side, we've got no charge, and 4 minus. So 4 minus on the right side. Which side are we adding our electrons to? Adding to the left side. And we need 3 to bring us down to a -4. And then we have to make our number of electrons equal between our oxidation and reduction half reactions. We've got 2 and 3, and those both multiply into 6. So our oxidation half reaction, we're going to multiply by 3. Our reduction half reaction, we're going to multiply by 2. You can probably see why there's lots of spots to make mistakes. All of the little balancing parts, and then we get to multiply everything, we get to add everything. It's very easy to make a clerical error and just forget to write something. To save us space, I'm going to do the multiplying and adding all in one step. I would not recommend this for you. So assuming that I did everything right, this should be, this purple block, this should be our final form. Then we want to go through and cancel stuff that shows up on both sides. That's going to be our electrons. The electrons should always cancel out completely. We also have water on both sides. You've got 8 on the left, we've got 4 on the right. So we can get rid of the 4 on the right, and that's going to get rid of 4 on the left. And so we'll be left with 4H2O on the left side. And then the last step is to go through and check everything. Iodine, we've got 6 on the left. 3 times 2 is 6 on the right. The next thing that shows up is hydrogen. We've got 4 times 2 on the left, so 8. And we've got 8 hydroxides on the right, so 8. We've got oxygen, 4 from our waters, another 8 from our permanganates. So that's going to be 12. On the right side, 2 times the 2 in our MnO4, plus 8 in our hydroxide. So we've got 12. Our manganese, we've got 2 and 2. And then for charge, really spilling over as much as possible into the next slide, we've got 6 minus and 2 minus, which is 8 minus. And on the right side, neutral, neutral, and 8 times 1 minus, for a total of 8 minus. Questions? And we're out of time, but there's one more slide left. This is going to be the hardest of the bunch. Should be the hardest of the bunch. So I'd recommend trying that. And then I'll post the annotated slides with the solution. I probably also went over it last semester, so you can go find last semester's video. It should be in there.